Right, welcome everyone. Thank you for coming, especially after yesterday's party. I know a lot of you did not have an easy time this morning. So welcome to my talk, Your Mitigations Are My Opportunities, or in its unofficial name, a bunch of separate things I did over the last few years that can be put together into one exploit. Where's my, there. So, start by introducing myself. I am Yarden, originally from Israel, but now from Canada. I work in Trail of Bits on the research team doing Windows work. Before that, I worked at CrowdStrike, and before that, SentinelOne, doing research, QA, automation, all sorts of different things. I'm also a circus artist. Up until a couple years ago, I was an employed circus artist. Now I am an unemployed circus artist. And before that, I was a pastry chef for a little bit. So after the talk, feel free to ask me about any of the broad range of topics. Now, I do security work, working at Trail of Bits, teaching Windows internals classes, including one here every year. Luckily, it was last week and not next week. I'm also teaching at Recon, Hexacon, a bunch of other conferences. So a lot of my time is doing Windows internals training, or mostly Windows-related work, specifically exploitation, post-exploitation, both offense and defense, so both exploits and mitigations. So let's talk Windows exploitation. Nowadays, Windows exploitation, just like on any other platform, is getting more and more difficult. There are more mitigations, there are more security tools, there are more built-in and third-party features making exploitation harder. Also, we're moving away from traditional mitigations to just fix a bug onto mitigations trying to kill entire bug classes, like cast guard trying to kill type confusion, like features such as address sanitizer trying to help find memory bugs, CET to kill ROP. Also Win32k being rewritten in Rust. So if at some point it's fully written in Rust, maybe it'll be just a little bit safer than it is today. Also a bunch of code integrity features limiting what you can run in user mode, in kernel mode. So you can't just go load any driver and have a rootkit or a bootkit, though some talks in this conference might make it seem otherwise. So we'll talk about a few separate things that we can put together to build one exploit. So looking at a modern hypothetical Windows system, which is fully patched, running on the newest hardware, newest software, we have a whole bunch of security features. So we'll see how we can start by being on a machine in user mode in a potentially low integrity process and make our way to the kernel, not just unblocked, but also undetected. So at first, we're in user mode, running in some low integrity process. Well, not even running yet, because we have some initial primitive that, let's say, allows us to overwrite the return address or overwrite data on the stack, but we need to turn it into code execution. Now, there's a bunch of features making this more difficult than it used to be, with the most recent one being Intel CET. Intel CET is the answer to a technique where you overwrite the return address to then return to your shellcode or return to a ROP chain, running instruction after instruction after instruction, all through return addresses. What CET does is it creates a second stack called a shadow stack that doesn't hold all the things a normal stack holds. Instead, it only holds return addresses. So when we run on our system, our usual stack is writable to our thread. We can put function arguments, local variables, return addresses, all the data we normally put in the stack. At the same time, the CPU holds a shadow stack, which we can't write into, only the kernel can, and it only contains the return addresses. So now, when we have a call instruction, the CPU pushes the new return address to two places. First one is the regular stack. Second one is the shadow stack. Then, when we hit the ret instruction, before returning to wherever we're going to return, the CPU will take those two addresses and compare them. If they're the same, all good, we're returning to where we used to be. On the malicious scenario, we had a call instruction push the return address to both stacks. Then an exploit comes and overwrites the return address with a fake return address, which in the pre-CET days or pre-CET systems would make the application reach the ret instruction and go back to whatever fake address you put on the stack. Now, instead, we hit the ret instruction, and the CPU compares the two addresses. It says that they're not the same, so it issues a new interrupt, int21. The interrupt reaches the kernel, which should terminate the process. And I say should because that is not necessarily what happens all the time. So in Windows, the implementation says we have a few exceptions to terminating the process. We don't necessarily terminate every single process that has a CET fault. Because, first of all, Windows is a very, very big believer in compatibility. So any process that does not enable CET, that is not compiled with CET support, will still have the CET fault because that comes from the CPU, but we won't crash the process. We'll let you go because, well, maybe you were compiled before CET, maybe you're not aware, maybe you're overriding the return address for some legitimate reason. So we're having backwards compatibility with old exploits, which is very nice of them. The second thing is a process may not want to enable CET or may only want to run in audit mode, which means we're not going to crash the process. We're going to send an ETW message for nobody to look at. Also, even if the process is fully protected, compatible, enables CET, unless it's running in strict mode, which Microsoft never documented, it can still load non-CET compatible binaries. And if you are returning to a non-CET compatible DLL, the system will allow you, because maybe that DLL doesn't know about CET, and maybe that DLL has a good reason to ROP. So you don't just have to find some non-CET process, you can also return to a non-CET DLL inside of a CET process. And my personal favorite, you don't have to return to your immediate return address. You can return to any address in the shadow stack. So as far as the CPU is concerned, you have to return to your immediate return address. But because of all sorts of operating system concerns and scenarios, Windows does allow you to return to any address in the shadow stack. So if you return to any address that was pushed to the shadow stack, Windows will go, okay, it will unwind the shadow stack up until that point, and you can return there. By the way, I was talking about user mode CT up until now, but all these exceptions also apply to kernel CT. In kernel CT, which is only enabled if a hypervisor is running, the shadow stack is protected by VTL1, only the secure kernel can modify it, and all those exceptions still apply. Now, for user mode CT, there are all sorts of additional features to prevent exploitation through APCs, through set thread context, through exceptions and exception unwinding. Kernel mode CT also has some additional features implemented in VTL1, but that's out of scope for this talk, so I'll skip it. So the bypass I'll explain now is not new. It's always been there in CT. I believe it also exists in other platforms as well, not just Windows. And you can return to any address that was pushed to the shadow stack. Now, people have known about it since CT was first introduced. So, for example, Saal, who may be here somewhere, mentioned it a few years ago when Alex Ionescu and I first published our CET paper. But I haven't seen any exploit use it. I haven't seen anybody officially introduce a POC. And I think it's really cool. So in the normal case, we have a function. This function, func A, calls func B and receives some class, some data structure. Now it takes that class and calls a function from that new class. So we're calling func B. Func B calls func C, which could be an initialization function. It could be anything. We don't really care what it does because we ignore its return value. Then we go initialize a new class and return it to func A. So we're calling func C. In this case, it returns 7, which we ignore. And we initialize our class, return it to func A. The class we initialized has a function called foo in the function table, so we go and call it. Now in the bypass scenario, we have the same func A, the same func B, but now func C doesn't just return a random value. Instead, it overwrites the return address, and it overwrites the return address with the address 2 frames back. So it ignores its current return address into func B and overwrites the return address with the return address of the previous frame into func A. So it will now be returning into right after the call instruction in func A, where we're going to use this new class. So it goes and initializes a different class that has a bunch of random data and also a pointer to a malicious function. And then it skips func B entirely and returns into the previous frame in func A, which of course will treat this fake new class as its valid class and call our malicious function. Now this scenario is of course more limiting than just overriding the return address with any shellcode or ROP chain you want, but it's still valid and it's still doable. And the more stack frames you have, the more you have to work with. So processes like processes implementing COM classes, browser processes, rendering processes that can have stacks with sometimes dozens or hundreds of threads will be more attractive targets than threads that have 4 stack frames. So you'll have more to choose from. This is also working in kernel mode. So in kernel mode, it's a bit of a more difficult target because normally kernel threads have less stack frames, so you have less to choose from, but you can still do this sort of type confusion in kernel mode as well. So onto the demo, I wrote a little executable that does pretty much what I just showed. This is a CT compatible system, so if I were to return to a completely incorrect return address, my exploit would crash. It's projected. All right. Okay. So I'm running my CT bypass test, and I've successfully diverted the execution, which you just have to believe. I can show you the code. I can share the code later, but like any demo on stage, you just have to believe that I did it. Now we've got some user mode execution, and now we want to get to the kernel. Getting to the kernel used to be super easy. You could just load a driver. That hasn't worked in quite a long time, and you had to start signing your drivers or get Microsoft to sign your rootkit. There is a whole process for that, but people still get rootkits signed. But let's say you don't have the right connections at Microsoft to sign your own rootkit. You need to use somebody else's. So the increasingly popular method is called bring your own vulnerable driver, where you use a vulnerable driver, either one that's already on the machine or one you bring with you. And a lot of times it's drivers that have known patched vulnerabilities, and you bring with you the old version of the driver that has known vulnerabilities. They might be years old, they have CVEs, everything, but they still load in the system. So you load the driver, you use the known vulnerability to overwrite things in the kernel, to disable things, to load your own rootkit, whatever you choose to do with it. But now we have HVCI, and the HVCI has a block list. HVCI is a feature implemented through the hypervisor that validates all the code running in the kernel. It all has to be signed. And also, it can't be any of the drivers in the block list. So HVCI has a pretty large block list with a lot of blocked hashes, blocked drivers, blocked certificates. So you can't load any of those. Which means that the bring your own vulnerable driver technique should not work anymore, only does. Because Microsoft isn't doing a very good job updating this block list. There is a new database called LOL drivers, living off the land drivers. It has about a little over 600 drivers in a GitHub repo. You can all go and download it. And when I did my testing last week on an updated system with the newest available block list, a little over 170 drivers on that list still loaded just fine. So you still have a lot to pick from. Some of those drivers are pretty well known, the ones that still load, and they load just fine, no problem. Also, even some of the blocked drivers, they're blocked by hash. If you get a newer version of the driver, it may load. Now, the newer version of the driver might be patched, but sometimes the patches aren't really all that great. One example here is the dbutil driver. It's a vulnerable Dell driver from 2008, 2009 that was running on every Dell system until about 2020, when me and about 15 other people reported a series of bugs to Dell. The driver had, if I recall, around 12 easy-to-find bugs and a few other bugs that were not as easy to find. And since then, it was used by the Lazarus group. I believe it was used by some other APTs as well. So of course, it's on the block list now, and there is a new patched non-vulnerable driver. Only it still is vulnerable. The only difference, and the reason I can share this on stage without reporting it to Dell or Microsoft or anybody, is that they made one change. They added a security descriptor. So now you have to be an admin to use any of the vulnerabilities. All the vulnerabilities are still there in the same ioctls, the same code will still work, but now you have to run as an admin, which is not such a huge block because with the bring your own vulnerable driver method, you already have to be an admin to load the driver. So assuming you're already an admin, saying, well, you have to be an admin to use any of the vulnerabilities is not such a big difference. So, all right. We got over CT, we got over HVCI. Now we have to deal with EDRs. As offensive researchers, our biggest problem with EDRs is the fact they exist. Our second biggest problem with EDRs is that they're getting pretty hard to disable. They used to be very easy to disable. There used to be lots of techniques. They're starting to protect themselves better. First of all, drivers are used, filter drivers are used to restrict access to the user mode process, restrict access to the service, restrict access to the files on disk or the registry. And also, the user mode process uses a type of protection called PPL, or Protected Process Lite. It's a special mode that only some Windows processes and some anti-malware processes can run in. And it's protected from every other process in the system that doesn't run with the correct protection level. Or sort of protected, because it's supposed to be fully protected from even admin processes and system processes, but there have been lots and lots and lots of issues with that. A few years ago, Alex Ionescu and James Forshaw did a talk showing lots of different ideas for PPL bypasses. There have been tools showing PPL bypasses. There was just a talk in Black Hat Asia by Gabriel Landau showing another bypass. A lot of those are using COM. James Forshaw published a few blog posts showing different PPL bypasses. Some of those bypasses are starting to get fixed, so there's now mitigations. Microsoft is starting to treat PPLs almost like a security boundary. Not enough to give CVEs to somebody who finds a bug there, but enough to try and block or patch some of the issues. Now, there are still ways to kill PPL, so I'm not going to show any generic PPL bypasses here, but there's some things we can do about specific PPLs or security products. So one thing we can do is to just disable the driver. Even if the user mode process still runs as a PPL, it needs information that normally it receives from the driver to detect anything. If the driver is gone, in some cases, the user mode process isn't going to run at all. And even if it does run, it will run without a lot of its data sources. So it'll have partial information at best and will not do a very good job detecting anything. Also, without the driver, the files on disk are not protected. A lot of the process protection is gone, so we can do a lot to just ignore it. So one fun way to get around drivers is to ask HVCI. If you ask HVCI nicely, it will block any driver you want. So you can't really extend the HVCI block list. It's on disk, it's signed, you can't mess with it. But you can use some undocumented HVCI features to do some interesting things. So a couple features worth knowing about, and they're all enabled through undocumented registry keys. One is audit mode, which is actually great for defenders, because if a system cannot or will not enable HVCI fully, you can enable HVCI in audit mode, so nothing will get blocked, but you will still get ETW events to the code integrity channel. And you can enable pretty verbose events, so you get sign-in information, you get hashes, you get all sorts of useful things for kernel events. The second thing, which is a bit more relevant for what we're trying to do here, is the HVCI disallow images. It's a registry key where you can put a list of driver names. So it has to be names of files on disk. And then at boot, HVCI will go and read that key and will block any driver on that list. So for example, I don't know if you can see this, it's a bit small, but on my work laptop, I have CrowdStrike. So the CrowdStrike Falcon was really messing with some of my research, blocking some of my attempts. I went and added csagent.sys, so the Falcon driver, into the registry list of HVCI disallowed images. I restarted the system, and Falcon won't load anymore because HVCI blocks it. So the message here says, code integrity determined that the module csagent.sys is not compatible with strict mode hypervisor enforcement due to it having an executable section that is also writable. That is a lie. It doesn't. That's just the placeholder message that HVCI uses for drivers it chooses to block through that list. So it doesn't actually have executable and writable sections, so it's just a placeholder message. So this will only block based on file name on disk, which means it is way more useful for offensive operations or just people trying to live their lives without an EDR looking over their heads and blocking their testing code. It's not really useful as a defense feature, because if you just go and rename the driver on disk, the blocking doesn't work anymore. But against EDRs, it's really great. It does require a restart, though, unless you want to use some kernel exploit to go and patch the list in memory. The list is saved in a global variable inside of CIDLL, but unless you want to go and patch the list in memory, there's no way to update it at runtime. You do need to restart the system for it. Unfortunately, this technique does not work against the Windows Defender filter driver, because the Windows Defender filter, wdfilter.sys, loads too early. It loads before CI initializes this list, so it's not going to be blocked by it. I've tried. But we have other ways to mess with Windows Defender. So one of the popular ways to kill a PPL, suspend a PPL, or just make it useless is to use some driver. So people have used the old Process Hacker driver, the old Process Explorer driver. They both had different capabilities that allowed killing or suspending or messing with PPLs. Now, the new versions of both of those don't have any of those issues anymore, but the old versions did, so different tools keep bringing them along to try and mess with PPLs like Windows Defender. Now, some of those, like the old Process Hacker driver, is now blocked by the HVCI block list, but even those that are not, there's another mitigation against them. That mitigation is in a driver called MSSecFLT, which is not a driver that's supposed to have mitigations at all. It's supposed to just be an informative driver supplying ETW events, but now it also has a mitigation as a part of Windows Defender ATP. So what it does is it uses the shim engine, which allows hooking all sorts of functions in kernel drivers. So Alex Ionesco did a talk about the kernel shim engine a few years ago. So it's a really, really interesting feature for a lot of different uses. But I haven't really seen it used for security purposes up to here. So now there's a new shim called KSE Sec, installed by MSSecFLT, and it hooks functions inside of drivers that might allow messing with a PPL. So it hooks ZW terminate process, PS suspend process, NT close, a lot of different functions, also ones that allow you to map physical memory. So it has two purposes. Now, by default, this won't do anything because it is running on your systems, but unless you're running Windows Defender ATP, the configuration says ignore, don't do anything, don't block anything, don't log anything. So this is the shim database, drvmain.sdb, and all those stars there are different drivers that get hooked by MSSecFLT through the shim engine. So this, again, it's a bit small, but this specific example is the Lenovo Diagnostics driver, which is hooked because it allows looking and mapping physical memory. So this shim operation actually happens through two drivers, MSSecFLT and MSSecCore. So MSSecFLT is the event provider. It logs different events into Microsoft Windows Sec. That's an ETW channel that anti-malware PPLs can register to get all sorts of different events for detection. MSSecCore is a new driver. It was added around 22H2. Depending on your system, it's shipped in a few different builds, and it acts as an extension. So having two drivers that have to talk to each other gives us some interesting opportunities that we'll use later. For now, we'll just focus on the shims. So what happens when your system starts? MSSense, the user mode process for Defender ATP, sends the required configuration to MSSecFLT. Tells it, we want to block calls to ZW terminate process if the target is a PPL. We want to log calls to NT-map view of section when the target is the physical memory device. MSSecFLT updates its internal configuration, and then it calls secbindhost, an exported function from MSSecCore. What that does is it registers MSSecFLT with MSSecCore and gets back a function table of a few different functions it's going to call. So it's this sort of private import-export mechanism. Then MSSecFLT takes a function from that function table and calls secregister kernel shim provider to register itself as the kernel shim provider. So MSSecFLT does not register any shims on its own. It asks MSSecCore to do it for it. It sends it the list of functions, and MSSecCore registers as the shim provider. Then, when we have some potentially problematic driver that gets shimmed by MSSecCore, let's say it calls ZW terminate process. So the kernel, before or instead of calling the function, will notify MSSecCore in its shim function sec KSE ZW terminate process. MSSecCore doesn't really do much with it. The main thing it does is it checks if it has a registered shim provider, and if it does, it will call the function requested by the registered shim provider. In this case, msec-flt. This whole thing is a private mechanism. It's not documented. It has a little bit of symbols, but not fully. But those drivers are not too complicated, so it's not all that hard to find the function table and the provider. So on the MSec core side, we have the officially registered shim function, which doesn't really do all that much. Mostly it checks if there's a shim provider registered with it, and if there is, it calls the function. That function is inside of msec-flt, which does a little bit more. Mostly it checks its internal configuration. Is this event even enabled? Does it care about this event? Does Defender ATP care about this event? Is it in audit mode? And then if it decides that it cares, it checks if the target is a protected process. If it's not a protected process, we can ignore it. We can forward the call as usual. If the target is a protected process, then we either block the call entirely or allow it, but log it to the Microsoft Windows sec provider. So, okay, let's say this is enabled with full protection blocking. We can't use any of the shimmed driver to tamper with a PPL. We have a plan B. MSMPENG is the user mode agent of Windows Defender running on all your systems unless you disabled it, and it is running as a PPL. So it's hard to suspend it, it's hard to terminate it, and we saw that we can't block WD filter from loading with the HVCI trick because it loads too early. So now we have to look at Windows Defender specific things and see what we can do about it. So when I looked at the Windows Defender filter driver, WD filter, I found a backdoor, because there is always a backdoor. The backdoor actually uses a really interesting mechanism. Usually, finding problems with drivers, you look at the IOCTL handler, you look at the user mode communication methods, specifically WD filter uses filter communication ports, but we can't use those because only the user mode engine can connect to it. You have to be a PPL, and there can only be one engine connected at a time. But it uses a different mechanism. WD filter is a filter driver, so it can register with the file system to register callbacks to be called when I/O operations happen. So normally filter drivers register functions for create operations, read, write, different I/O operations. WD filter also registers a callback for a mechanism called FSCTL, which is like an IOCTL, but for file system drivers. So file system drivers can also receive special requests, which special requests depends on the file system driver, where you open a handle to any file on that file system, and then you can send an FSCTL to that file. Now that won't actually get to the file, that will get to the file system driver, which will do whatever you asked it to do based on the IOCTL code. WD filter registers callbacks for FSCTLs as well, so it wants to get notified before an FSCTL happens. So it can monitor, it can block things if it wants to, it can modify the requests. But inside of that FSCTL handler, that again does not get called, the FSCTL is not aimed for Windows Defender. The FSCTL is aimed to your file system. But on the way to the file system, WD filter captures it and looks at it. And inside of that handler, there is one check for an FSCTL code that doesn't exist in any file system. No file system implements this code. If you look at the SDK, if you look at the official definitions, this code is not defined anywhere. This code, 902EB, is not a completely made-up code. It's part of the regular FSCTL numbers, just nobody implements it. Only Windows Defender does. And when you do an FSCTL to your regular file system with this code, Windows Defender captures it and checks, are you my engine process? And if you're not my engine process, am I in a special state called panic mode? Now, panic mode, before knowing anything about it, panic mode already sounds fun. Our whole goal is to mess with EDRs. Making an EDR panic sounds good. We can start there. So panic mode is a mode that the driver enters when it asks the user mode engine to scan a file, and it times out too many times. So if it times out, the default configuration is 4 times, the driver will enter a panic mode where it opens this special FSCTL backdoor to anybody. So anybody can call this FSCTL and get to a special interface in Windows Defender. Now, entering panic mode is not that easy because the default timeout Windows Defender uses is 4 minutes for local files and 6 minutes for network files. So getting that to timeout is not all that easy, but if you can get it to timeout a few times, the driver will enter panic mode. What can you do in panic mode? Well, here we have the FSCTL handler. It gets called when you send an FSCTL to a file system. And we have this FSCTL code, 902EB, which then checks, first of all, are you my engine process? We're obviously not. We're trying to kill it. Second, it checks some internal flags that we can't modify, only the engine process can ask to modify them. And then it checks, are we in panic mode? And if we've successfully entered panic mode, we get a call to MP FSCTL dispatcher, which is this internal interface. It has a few interesting functions. The one most relevant to us at this moment is MP terminate engine process. That does exactly what you think it does. The driver goes and terminates its user mode process. So what we need to do is we need to get it into panic mode. Then we need to send this FSCTL with the right code, which is 9. So if you send code 9, the driver will then go and terminate the user mode process. So I did this with a debugger and 2 lines of Python. A debugger mostly just to shorten the timeout time, so we don't stand here for 15 minutes waiting for panic mode to start. So I use the debugger to shorten the default timeout to a really, really short time, so it times out almost immediately. And 2 lines of Python. In the first one, I just open a file handle to a file on disk. The file can be any file, it doesn't matter. It just needs to be some file on the file system so we can send an FSCTL that will be intercepted by Windows Defender. Then I go and send an FSCTL with the magic code and an input of 9, because I want to access function 9 to terminate the user mode process. So for the demo, I will not try to do it live on stage because me and the demo gods are not on good terms. Instead, I did this yesterday and took this video. So here we're starting with magic kernel addresses. Those magic kernel addresses are inside of the global structure that Windows Defender uses to manage its configuration. It's called MP data. It's about a page long. It contains all of its internal configuration. Here I saved 3 different addresses. One is the timeout, so I can edit it to be a short time. By default, it's 4 minutes. And then looking at 2 other values, just to know when panic mode gets enabled. One is panic mode. The second one is a count of how many times we've entered panic mode. So we need both of those to be set to something that's not 0, and then we know we've entered panic mode. So I go and I edit this timeout to be 5 milliseconds, just because 5 milliseconds will make it time out almost immediately. Then I go and check the new values of panic mode, and in the background, you'll see Windows Defender updating itself a few times, writing new Yarden definitions against what I'm doing at this very moment. I mean, not really, but I'd like to think that. And panic mode is enabled. Now, if we look at System Informer, we can see the user mode engine, MSMPENG. I open my Python that already has a file handle open, run the command, and when we're back in System Informer, the engine is gone. So the engine went and not terminated itself, the driver terminated it. Now by default, the service will try to restart itself a few times. So the win-defend process has recovery options where it will try to restart the service 3 times. So you will need to either change this or just get the driver to kill the process 3 times in a row, and then it gives up. So up until this point, we've bypassed CET to run our user mode code. Maybe we've used it in the kernel as well. We found a way to elevate ourselves into the kernel through one of the many vulnerable drivers that are still allowed to run. We bypassed whatever EDR is on the system we're working with, and now we're in the kernel. But we're not done, because the kernel is a very visible place to anybody who's looking. Loading a driver will show up in all sorts of different lists. You can't just patch anything you want because of PathGuard, HyperGuard, all sorts of different things that are looking for you and are looking for any evidence that something malicious is there. So we want to find at this point something that will help us, but also not be visible to forensic analysts, to security tools, to built-in security features. So I like to use internal mechanisms that I can override and hook to implement whatever I need at that moment. So we can go back to MSSEC FLT and MSSEC Core and use their private communication mechanism to implement our own private communication mechanism. So having 2 drivers that talk to each other is great because there are function tables. Function tables are always great for offensive researchers. You can have a lot of fun with function tables in a lot of different ways. In this case, we can take those 2 drivers and we can edit the function table. So earlier I showed how the whole registration works. MSSEC FLT registers itself as a shim provider in MSSEC Core. MSSEC Core now has this function table of functions that it's going to call every time a shimmed driver does any of the operations that were hooked. So let's say we are a rootkit and we go and find this internal mechanism, we find this function table, this extension in MSSEC Core, and we redirect it. So now instead of calling MSSEC FLT, we now call our own driver. So now every time somebody uses a shimmed driver to call ZW terminate process, instead of calling into the MSSEC FLT, sec KSC ZW terminate process, it will call our driver. Now we can use that to not just completely make this mitigation useless, we can use it to implement our own communication mechanism, or at least a one-way communication mechanism, where our user mode process can go and load, let's say, the old Process Explorer driver and send it a request that we know calls one of the shimmed functions. Let's say nt-close or ps-suspend process. Now ps-suspend process gets sent to, ps-suspend process gets called in the kernel. The kernel goes and sends that operation and calls the shimmed function in MSSEC Core, and MSSEC Core calls its extension routine, which is in our driver. So we can build an entire limited but still existing communication mechanism around functions that we know are hooked in drivers that are shimmed by those drivers. And nothing will look at it because it's an internal communication mechanism. Nothing knows it's there. Nobody knows it's there. Even if they do, they wouldn't know where to start looking. No tool looks at it. No forensic analysts look at this. And you can have your own very well hidden communication mechanism just built around an existing thing. Now, this is, of course, not the only example. We can do that in many different drivers, many different mechanisms. Can do it with extension hosts, with callback objects, with all sorts of different things that have the same functionality overall. But I think this is a fun example. Also, I have a long-running project of writing a demo rootkit using entirely Windows Defender mechanisms. So this is part of a long-term project. But you can use a lot of different drivers. Also, in some systems, this mechanism doesn't exist because everything is implemented only in MSSEC FLT. With MSSEC Core, they shipped it, and then they removed some of the shim functionality. Possibly they discovered that they're not supposed to use undocumented features in their own EDR. So they shipped it, and then they removed it, and then they shipped it again. But in some systems, it's only in MSSEC FLT. So it is a bit of a mess. So whether or not this works does depend on your individual systems. But this model will probably ship entirely at some point. So, to summarize, we've had a few different steps here to achieve our exploit. We got to a machine where we have CET enabled, and instead of finding a process that doesn't enable CET or something like that, we went and bypassed CET by returning to a completely different address, but one that is still in the stack. So we've created some sort of type confusion to achieve code execution. We reached the kernel through a vulnerable driver, one of the many that are still allowed. And then we used either HVCI or some internal mechanism in the specific EDR we're looking at to block the driver or kill the PPL. Now, this backdoor thing exists specifically in Windows Defender, but a lot of EDRs have all sorts of internal debug modes that maybe should not have been released in release builds, but they are. So those get discovered once in a while. So we found a way to kill or neutralize the EDR some way. We got to the kernel, and then in the kernel, we are doing our best to hide ourselves by patching existing mechanisms and systems to not be as visible as we would normally. Or we just stay in user mode where it's nice and hidden, and just use our vulnerable drivers to do whatever we want in the kernel on a one-off basis. Now, we finished a little bit early, so we have some time for questions if you have any. If you don't, I'll be around all day. Feel free to come and ask me. All right, if there are no questions, I'll be around. You can come ask me questions later if you have any of them. Oh, yes.
So I'm a C++ programmer. So for the shadow stack thing, I was thinking maybe it's because you have to make long jump work. So you have to be able to jump back multiple stack frames. And that's probably why they have to do that.
Yeah, the specific choice around returning to any address on the stack is really around long jumps and exception unwinding and things like that. So it is necessary, but it also allows us to do this type confusion thing.
No, it's cool.
All right, thank you everybody, and see you around the conference today.